this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering. And I'm going to deal with the course Computational Aerodynamics. And today's lecture we'll see types of grid and boundary conditions. Before that, we'll recap what we had seen in the previous module. So we had seen introduction for computational dynamics, why computational dynamics, and we had seen that there are two different approaches before the CFD tool has evolved. So one is pure experiment, and the other one is pure theory. And so the problem is that for the experimental setup, the cost will be very high, and analytical approach, which is pure theory, so will be done for only simplified problems, but for complicated problems we cannot do. So therefore, a new approach, so which is computational fluid dynamics. So it is a tool which will solve the governing equations of fluid flow mathematically, okay, using approximate numerical methods, and will give a solution which is near to the exact solution. Okay, so this is all about CFD, and we have seen the process involved in the CFD. So we have to take what is the fluid problem, then physics of the fluid, and the Navier-Stokes equation. So which type of equation? So then we need to discretize the form. Then we have to select which type of grid. We'll see it in today's module. So what are the types of grid, and so whether we can have spacing uniform or non-uniform, and then after the solving the numerical solution, then you will get the results. Okay, so this is what we have. So these are the governing equations which we had seen. So in order to solve any fluid flow or heat transfer problem, so these three equations are used. So basically, these three, whatever it is written, so it is the first continuity equation and energy equation are written only in scalar form, whereas momentum equation, actually it is written in vector form. So basically, continuity and energy equation, they are like scalar, and the momentum is vector. So you can see that the equation 2 is written in the form of vector notation. So here, if you want to write the second equation, which is momentum equation in scalar form, so you will write in the form of x momentum equation, y momentum equation, and z momentum equation. So therefore, one continuity equation and three momentum equations scalar, and one energy equation. So total we have 5 governing equations. But the problem is that we have only like 5 equations, but more parameters. So let's say what are the fluid properties we have? It's like density, u velocity, v velocity, w velocity, pressure, and temperature. Okay, let's say here you can see you have 6 variables. Let's say you have 6 variables. So 1, 2, 3, 4, 5, 6. So but you have only 5 equations. Okay, so therefore, if you have only 5 equations, and if you have 5 variables, so we cannot solve for pressure or velocity or temperature. We cannot get the values. So what we do is like we will add some extra equations. Let's say you have perfect gas equation, P is equal to rho RT. Okay, so if you are keeping on adding equations, like you will get more additional variables. So the solution for this kind of equations is like, so first we need to make some assumptions. So which type of fluid we are solving, so whether it is a compressible flow or incompressible flow or steady flow or laminar flow, inviscid flow, viscous flow. So depending upon the assumptions, so the equations whatever we have, so it will be reduced. So for example, so if the flow is steady, so you don't have this term, you don't have time derivative terms, and if the flow is incompressible, so the density term will go off. So density is constant, so therefore the equations whatever we have, so one of the variable will get reduced, so the density will be constant. So you have u, v, w, p, t. Okay, so you have 5 variables and 5 equations. So basically, so this is how we do approximations and solve the governing equation. So here the task of CFD is basically you have a partial derivative here, dou rho by dou t. So this dou rho by dou t has to be written in algebraic form, in linear form, and solve the parameters actually. So there are different types of approaches. So what we gonna see in the CFD. So how do we actually linearize, or sorry, replace this partial derivative with in algebraic form, and what are the types of methods available? So we will look in this module. And we had seen some examples of external flow, so which is flow over wind turbine, and internal flow. So we have particles rotating with certain angular velocity, and we had seen different types of approaches for the fluid flow. So we had seen Eulerian approach and Lagrangian approach. So for the Lagrangian approach, so what we had seen is like tracking of each fluid particle. Okay, so basically you need to get the parameters, so flow parameters of each fluid particle. So how it is behaving with respect to time. Let's say you have velocity u of x comma y comma z comma time. Okay, and so this thing is for an single particle. So if you are tracking of a single particle, then the approach whatever we are doing is like Lagrangian approach. For example, if we are doing for an average property, so let's say you have a cross section here. So if you are getting the flow property, so let's say pressure at this cross section, velocity at this cross section. So this is all about the average properties of the fluid at a particular cross section or a particular area. So this is what we consider. So the average properties that we take. Okay, so these are the two different types of approach. So basically, in the Lagrangian approach, we cannot take our governing conservation equation. So Boltzmann equations are used. So in this course, we are not going to see the Lagrangian approach. So basically, we are interested in the Eulerian approach, and we will see how we can derive the governing equations for a particular problem, fluid problem, and how can we go for the CFD approach. We'll be seeing. So we will be sticking to the Eulerian approach. So basically, Lagrangian approach is used for space. Let's say higher altitudes of the Earth's surface. So the density is less, and the fluid particles, whatever we have, will be having a large distance between molecules. So that is why in those cases we will use the Lagrangian approach. But in the Eulerian case, so there is continuous distribution of fluid particles. So if you take a sample space, so you have more number of fluid particles which are present in this sample space. But if you take in the Lagrangian approach, if you take sample space, so you have one fluid particle here, other fluid particle here, other fluid particle here, other fluid particle. So they are very far away. So in this approach, like in this problem, so we will use the Lagrangian approach. But here in this problem, we'll be using the Eulerian approach where you have continuous distribution of fluid particles. Okay, so this is what we have. And in today's lecture, we'll be going to see what are the types of grid we have. So basically, there are two types of grid. So you have a structured grid and you have unstructured grid. So first, we will see what is structured grid. So basically, the meaning of structured grid is, so here you have lines which are going along x direction, and you have lines which are going along y direction. So there are more number of, so if you see, basically it's a square, sorry, it's a rectangle section. So in the rectangle section, so you have subsections. So it is divided with respect to lines which are going along x-axis. So parallel lines, all lines are parallel to each other, x lines, and you can see y lines which are parallel to each other. So here the terminology of a grid is like the intersection of these x lines and y lines is nothing but a grid point or a node point actually. Okay, and here in this picture you can see basically what we have is a structured grid. So why we had named it as structured grid is because, so you have cells like a quadrilateral kind of thing. So quadrilateral which is having four sides. So basically here it can be a square or it can be rectangle. Okay, so and the main thing is that so the x lines, so the grid will have x lines and y lines. So no two x lines will meet each other at any point for a structured grid. So if it is meeting and going, so then you will have negative volumes and you will have error when you are framing the grid. Okay, so this is what we have, and you have y lines actually. So even here you have y lines, so you can see these y lines also are parallel to each other, and x lines also they are parallel to each other. So the combination, so when these two x and y lines will meet each other, so the intersection point is nothing but grid point. Okay, and if you see the entire figure, so the perimeter section, so whatever the thing we have, so we call this is a domain actually. Okay, so fluid domain. So basically the domain is the boundary of the entity. So here you have this boundary, so we can say it is a rectangular boundary, and here and inside the boundary or inside the domain there are subdomains. So even if you see inside the domain, so you have these square or rectangular shaped or the quadrilateral shaped entity. So basically the boundaries of the entity is called domain. So inside the domain, so with the help of mesh or the grid, so we will divide the domain into subdomains. So basically all these square shells or the rectangular cells or the quadrilateral cells which we have here, so basically these are called subdomain cells, or let's say cells or the node cells. So whatever, there are different terminology. Okay, so the first the smallest entity of this structure is like you have first a grid point. So the combination of all these grid point will give rise to a cell. Okay, so there are so many number of cells and so many number of grid points. So you can see so many number of grid points that we have. Okay, and here you can see basically it is a 2D structure. So whatever we are seeing, so basically it is a 2D structured grid. Okay, and now if we see there are grid points which are on the boundary also, and whatever the entity we have, the edge lengths. So here you can see this is one edge length, and this is one edge length, and this is one edge length, and this is one edge length. So we have four edge lengths. So basically for this entity, so we have four edge lengths. So we call it as four boundaries actually. So for these boundaries we need to give conditions. So that's why these are called boundary conditions to simulate the fluid flow. Now we will actually see in detail in the further lectures. So what in detail different types of boundary conditions we have. But here let's have a glance about what type of boundary conditions can be given for this edge lengths. Okay, so let's say if we want to simulate flow over a flat plate, what we have is like we will have a flat plate, and on that flat plate we need to create the airflow. So this is what we need to do. So for that case, so what we will do is like we need to give realistic boundary conditions to simulate the real flow phenomena. For this instance, so here you can see on the bottom surface, so you have an entity. So this one is called a wall. So basically we have to give this condition as a wall condition. So basically what is the meaning of wall? There is no penetration of the fluid, and there is no flow passes perpendicular to the surface. So whatever the flow that is coming and striking to the surface, it will actually stick or it will reflect. So that is what we have for the wall conditions, and this is a realistic condition. So in real, so if we have a flat plate, so if the flow is coming and hitting the flat plate, it will come so near to the boundary. Some of the flow will be sticking because of viscosity. Other fluid will be actually moving with certain velocity. So those kind of conditions actually we need to give. So when we are giving a boundary condition as a wall, so there are two kinds. Like you have a slip wall and you have no slip wall. Okay, So the meaning of no slip wall is, so if you have a fluid particle, so here, so the first layer of fluid particles which are near to the flat plate will actually stick to the wall actually. So there is no the relative velocity between the wall and the fluid particle will be zero actually. Okay, so here the first fluid particle which is near to the wall will have a zero velocity. So the next fluid particle will have some velocity. So likewise, so other fluid particle will have some increase in velocity. So in that way, so it will increase its velocity. So because of viscous phenomena and because of the viscosity effects which is present near to the wall and the fluid particle, so the first fluid particle will stick to the surface. So this condition is nothing but a no slip condition actually. Okay, the first fluid particle which is coming and hitting the wall surface, so will stick and it will not move. So this is called no slip condition. And the slip condition, a slip wall is nothing but, so these fluid particles will not stick. So this will move actually. Okay, so this kind of condition is nothing but a no slip condition. So there are other conditions you can give for the wall, isothermal temperature constant wall, or you can give adiabatic wall, or you can give a heat source, heat generating wall. So you can give a number of conditions actually. And here if you see the left boundary, so basically on the bottom surface of the edge, so we have given this as a wall boundary condition. So here we can actually take flow from right to left or left to right. So conventionally we will take so this as x and z axis. So this is called positive z axis and this is called negative positive y axis. So we tend to take the flow from left to right. Okay, so that's why, so what type of boundary condition that we give for the left wall is like you have to give inflow, okay, or the inlet boundary condition. Okay, so we say that it is inlet. So basically the flow will actually go from one region to other region because of pressure difference. So the pressure here, if it is, so let's say this is P1 and here it is P2. If P1 is greater than P2, then flow will go from left to right. So if P2 is greater than P1, so the flow will go from right to left. So this is what we have. So purely because of pressure gradient, the flow will go from one region to other region. So you can give pressure inlets, or you can give velocity inlets, or the velocity inlet and pressure outlet, or the density based or the mass flow rate. So there are different types of options which are available, so which we'll be looking in detail in further lectures. But meanwhile we can see here you have velocity inlet actually. So let's say we are taking velocity v is equal to 1 meter per second, okay, or u is equal to 1 meter per second. So we take that only x velocity, which is nothing but u velocity, is present. So here the left boundary is finished, so and the bottom boundary is finished. So on the right one, so we take this as outflow or outlet actually. So basically what we call it as outflow or outlet. Okay, so in this outflow or outlet, so what we have, so the basic thing is like, so here the flow has to leave, which is entering from left surface or the left boundary, and it has to leave at the right boundary. Okay, so that's why we are giving an outlet or outflow boundary condition. Okay, so this boundary condition, whatever we have, so we can give as a pressure outlet, okay, or we can give vacuum pressure. Okay, so there are other boundary conditions, so which we'll be looking in further lecture. And on the top boundary, so since we have finished with the bottom, left and right, so the top one what we take is like far field or free stream. So basically the meaning of far field or free stream what we have is, so the flow which is present near to the wall or the flat plate will be affected because of presence of the fluid. Okay, and because of presence of, so basically what is happening is, initially let's say you don't have any object in the airflow. So what happens? Air will have, let's say, uniform flow or any other kind of phenomena. If because of presence of the flat plate, what happens? It will stop some fluid particles. So because of presence of flat plate, so the pressure and velocity, if it is compressible flow, the density phenomena, so will be changing. So we need to capture, so what are the changes that are happening over the body because of presence of flat plate. Okay, so the far field or the free stream region is a region where the because of the presence of flat plate, the flow properties will change to certain extent. After that extent, the region of in the far field, so there is no variation of these properties. So the far field is a region where the flow properties are not affected because of the presence of the body or the flat plate. So therefore, we need to give a region called or the boundary name called far field. So the major important thing that we have to take is like, so how much length or how much height that we need to take so that this region is undisturbed. Okay, and one important thing is like you need to capture everything, and you need to actually see that nothing is missing while doing the CFD analysis. Okay, so here if you see the zoomed view of grid, so what we have here, you have the boundary grid node point. So these are the boundary points actually. So what we are doing before starting a CFD problem is like we are performing this grid and mesh, and then we apply boundary conditions, and then we will discretize the equations, and then we'll apply the matrix inversion, solve them, iterate them, and get the results. So this is what we have now. So how do we get the values? So basically there are two different kinds of approach what we do. So finite difference method and finite volume method. We'll see what is finite difference method. So basically, as I told you, so these are the x lines, okay, and these are y lines actually. So the intersection of these x lines and y lines, what we have is the grid point. Okay, so these are the grid points. Okay, so the governing equations, so whatever we have, continuity equation, momentum equation, energy equation, so these equations are solved at this grid point actually. So what we do is like, so we will actually we will actually linearize these partial derivatives. Let's say you have dou rho by dou t at this, so at this grid point you will discretize them, and you will linearize them. So if you have three equations, let's say at a particular grid point, you will actually linearize or discretize three equations. So let's say we are seeing in this region. So how many grid points we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So total we have 9 grid points. And if you take, let's say you have three equations, so 9 into 3, so basically you have 27 actually total 27 equations actually. Okay, so what we do is like we will give numbering actually. So 1, let's say this is 1 comma 1, and this is 2 comma 1, and this is 3 comma 1. So similarly you will give the notations. Let's say what we have here is here you have 1 comma 2 and 1 comma 3, let's say. So these notations you will give. What we do is like we will solve the pressure, density, velocity, temperature at 1 comma 1, 2 comma 1, 3 comma 1. Similarly 1 comma 2, 1 comma 3. So all these governing equations are discretized at this grid point actually. Okay, so this is nothing but finite difference method. So we will be seeing what is finite difference method in detail in the further lecture. But meanwhile, so see, you assume that, so what we do is like, so whatever the governing equations that we have, so these partial derivative terms will be linearized or formed algebraic way at the node or the grid points. Okay, so these are nothing but the boundary points. Okay, so at this boundary, so basically you will apply some condition. So let's say here velocity is 0, so this value is known, this is unknown, so will be calculated with this value, so with the initial values. Okay, so this is what we have. The importance of boundary conditions is like, so boundary conditions and initial conditions is like to have initial values or the boundary values to solve the fluid flow problem from the initial conditions. Okay, so here you can see there are grid points. So you have 1, 2, 3, 4, so on. So the distance between two grid points is nothing but the spacing, actually grid spacing. So here you can see what is the spacing? It is delta x. So why? Because let's take this is along x-axis and this is along y-axis. So what we do is like, so the distance between one grid point and other grid point, what we have is delta x along x-axis, and the distance between one grid point and other grid point along y-axis is delta y. Okay, similarly along z, if you take z direction, you will have delta z. Okay, so delta x, delta y and delta z. So it is called the grid spacing or the mesh spacing what we have. So nodal spacing, so we call it as a grid spacing, let's say. So the grid spacing can be uniform or non-uniform depending upon the fluid flow phenomena or depending on the application what we take. So here you can see what is the meaning of uniform spacing. So let's say these three things. So 1, 2, 3. So the distance between 1 and 2, let's say it is delta x, and if the distance between 2 and 3, if it is same delta x, so and if it is distance between 3 and 4, if it is same delta x, so what is the meaning? So the spacing is uniform between successive grid points. So then this type of mesh is called uniform mesh. Okay, and you can see basically this smallest entity, this is called cell actually. Okay, grid cell or the mesh cell, whatever we call, and this cell is constructed with the help of 4 grid points. Okay, so if the grid points, if the delta x, so whatever the spacing between two successive grid points is same as delta y, so what is the meaning what we have? So delta x, if it is equal to delta y, so what is the cell shape? So we have the cell shape as square. Okay, so each and every cell, it is square shape, and this type of phenomena is called uniform grid. And one more thing, so this spacing of these two, delta x and delta y, can vary in successive distances. You can vary the delta x position along x-axis, or you can vary delta y position along y-axis. So depending upon your interest actually. There is no rule that if delta x is varying, delta y has to vary, or the delta y is varying and delta x has to vary. These are independent actually. These are not dependent. Okay. So this is what I am talking about. So here you have non-uniform grid along x-axis. So the meaning is like non-uniform is the spacing between two successive grid points is not same. So what I'm talking is about along x-axis. So here if you see, let's say this is our origin, okay, O, and this is at length L, and this is along x-axis, and this is along y-axis. So what we have along x-axis, so from the origin, if you see till the distance along L, so the spacing between two successive grid points are not at all same. Okay, so if you take, let's say this is our interest, and this is our, let's say this is our interest, and this is our interest, and you can see this is our interest and this is our interest, and here you can see this one and this one, here you can see this one and this one. So if you see 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's say this is delta x1, delta x2, delta x3, and delta x4. So delta x1 is nothing but the spacing, grid spacing between 1 and 2. 3 and 4 is nothing but let's say x2, delta x2, and 5 and 6 x3, and 7 and 8 you have x4. So the distance between these grid points, so delta x1, delta x2, delta x3, and delta x4, these are not at all same. These are not equal actually. So why? Because the spacing between two successive grid points are not at all equal. So that's why these are not equal. If these are equal, what happens? So we call them as a uniform grid along x-axis. So since the spacing between two successive grid points are not at all equal, so therefore what this kind of mesh is called is non-uniform mesh and or non-uniform grid. And this is only along x-axis that we are talking. So next we will see for y-axis also. So here what I am doing is like here only along x-axis the grid is non-uniform, and here it is only along y-axis the grid is non-uniform. Here you can see what we have. So let's take this is our point, this one and this one and this one and this one and this one. So 1, 2, 3, 4, 5, 6. So let's take this is delta y1 and this is delta y2 and this is delta y3. Okay, so what is happening? Delta y1, delta y2, delta y3. So the spacing between these these things are not equal actually. So if you take 1 and 2 and if you take 3 and 4, if you take 5 and 6, so the successive grid point distances, okay, is not at all same. So therefore what is the condition? So delta y1 is not equal to delta y2 is not equal to delta y3. So if delta y1 is equal to delta y2 is equal to delta y3, so then this condition is nothing but a uniform grid along y-axis. So this is uniform and this is non-uniform. Okay, so this is non-uniform and this is uniform grid along y-axis. So here we have taken non-uniform grid example along y-axis. So this is the case where you have this non-uniform grid, so both along x-axis and y-axis. So in the previous slides you can see only along x-axis I have varied the grid, okay, independently, and here only along y-axis I have varied the grid spacing, and here in the third case, so the non-uniform grid is both along x-axis and both along y-axis. Okay. So here you can see that more number of grid points are clustered near to the left and the bottom boundary. Okay. So here you can see the spacing. Here if you see the grid cell and here if you see the grid cell, so they are entirely different. So here if you see and here you see they are entirely different. So this is the case what you have the non-uniform spacing. And for the uniform spacing, all the cells will have an equal shape. Okay. And other entities that we have is like coarse grid and finer grid actually. So basically the meaning of coarse and finer grid is, so let's say in this grid point, in this, so this is one domain, domain 1, and this is domain 2. Okay. So what kind of mesh it is? It is a structured mesh and with uniform spacing, let's say. So here also you have uniform spacing and here also you have uniform spacing. So the difference between the domain 1 and domain 2 what we have is like you have more number of grid points in the domain 2 and you have less number of grid points in the domain 1. So if you have more number of grid points, then it is called a finer grid. So if you have less number of grid points, then it is called a coarser grid. Okay. So here we will see basically why we will use finer grid or why we will use coarser grid, and can we use some area coarser and some area finer also. We will see in other examples also. The thing is, let's say we are interested to see the flow over flat plate. So what we have is like this is flat plate. Okay. So on this flat plate we are performing this mesh. Okay. So let's say you have 10,000 grid points. Here you have, let's say, 1 lakh grid points. Okay, so what happens? So basically the difference is, so here you need to solve let's say how many equations? Let's say 30,000 equations. Here you need to solve 3 lakh equations. The difference is, so here the computational cost is less for the coarser grid and the computational cost is more for finer grid. Okay, but the accuracy of the solution will be very high for the finer grid and it would be low for the coarser grid. But sometimes, so we need to perform a grid or the mesh independency study where you have to decide what is the minimum grid points where you can get your accurate solution or the approximate solution near to the experimental results. So this is what we have to do. Okay, so it's not like you have to use every time finer grid or it's not like you have to use every time coarser grid. So what we have, let's say you have flow over flat plate, you have experimental results. So let's say here the velocity is 1.45, which is coming from experimental result. Okay, let's say this is experimental result. So you have to perform grid, you have to perform mesh for different times. Let's say initially use 10,000. So you have to go double it, 20,000, 30,000, let's say 20,000. Okay, next you will go 30,000. Okay, so let's say at each and every grid point you will have solution. Let's say here this is U1. So the velocity has come 1.39. So here for the U2, let's say the velocity has come 1.446. So here it has come 1.448, let's say. So what I'm saying is like U1, U2 and U3. So U1 is nothing but the case where you have 10,000 grid points. So U2 is nothing but the case where you have 20,000 grid points. U3 is nothing but the case where you have 30,000 grid points. So the thing is, so you have approached a near value to the experimental result, which is 1.45 with certain error, which is very less. So there is therefore 20,000 grid points would be enough to solve this flow over flat plate example. It's not worth that we will have to go for 30,000 grid points. Only 20,000 grid points would be sufficient. So here, in this case, what happens? The 10,000 grid is a coarser and 30,000 would be the finer grid. And here the 20,000 grid point would be a medium level grid. Okay. So this is what we have. And the other type of grid what we have, it's called unstructured grid. So here you can see the cell. So the cell, whatever we have, it is of triangular shape. It's not no more quadrilateral. The thing is, so let's take this is our node of interest and corresponding to this node, so there are so many number of grid points are attached to each other. Whereas if you take a structured grid, what happens? Surrounding to this, let's say this particular grid point. So this particular grid point, so you have certain finite set of grid points. But in the case of unstructured grid, so there are so many number of grid points attached to a particular grid point. So they depend, let's say here what I'm saying is, so if you have this is grid point, so the nearest grid points are countable and you can easily access. But here in the case of unstructured grid, so if you take this particular grid point, so there are so many number of neighboring grid points. Okay, and one important thing is like, so you will have so many number of grid points for an unstructured grid when you compare it to structured grid. Therefore what happens? You need to solve more number of equations and therefore what happens? Your computational time will be higher. Okay, but when can we use the structured grid and when can we use unstructured grid? We will see. Okay, so here this is an example where you have unstructured mesh on the complex geometry. So if the boundary of the domain of the object, what we want to see, let's say if you are seeing flow over flat plate, it is a regular object, there is nothing curvature and it is simple. So for these simple entities, so you can perform a structured grid. Okay, so for this entity you can perform structured grid And but for this entity, what we have, so since you have a curvature and this is somewhat complex, okay, so for this entity, like it is better to perform unstructured grid. But here also, if you can perform structured grid, but you have to take very special interest, and you have to divide the domain into sub domains, and you have to perform sub meshes, okay, and then you can perform some area structured mesh and some area unstructured mesh. So therefore, the combination of some region structured mesh and other region unstructured mesh is called the hybrid mesh. Okay, and here you can see an example where near to the boundary you have a finer region where you have more number of grid points, and away from the body you have coarser region. Okay, so why? Because so the our area of interest where we need to see the fluid flow phenomena is near to the airfoil or the wall. So these variations are very important to us compared to this one. So therefore what happens, so you need to perform a finer mesh near to the boundary. Okay, so you need to perform a finer mesh near to the boundary. So this is why we had seen initially a coarser mesh and finer mesh, uniform mesh, non-uniform mesh, both along x-axis and along y-axis. So here you can see an example where the hybrid mesh can be used, the combination of structured or unstructured. And the thing is that so depending upon the boundaries of the object what we are doing the CFD analysis, the type of grid will vary. So if the boundaries of the body is regular, let's say flat plate or a pipe, or let's say any car, if it is a not a complex body, so then you can perform a structured grid entity. If you have a curved object, if you have a complex object, okay, so then for those cases you can go for unstructured mesh. Why? Because so if you have a curved region, so let's say on this curved region, so when you are doing this structured grid entity, so these two y lines may intersect and form negative volumes. Okay, so this is why actually the structured grid is not advisory for any curved objects. Okay, so thank you. So with this lecture, so we would end the topic grids. Okay, in the next lecture we will see in detail what type of the boundary conditions that can be used in detail. What are the different types of boundary conditions available depending upon the problem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.